In previous videos, we saw how to find the projection of a vector onto a subspace if you had an orthogonal basis for that subspace. Now we're going to do it even if we don't have a orthogonal basis, and this is going to give us the machinery we need to do least squares. So let's suppose we have a vector space V, and we have a subspace W which has some bases B1 through Bk, so it's a k-dimensional subspace, and we have some vector in V. And our problem is we want to project x onto W in an orthogonal way. That is, if here's W and here's x, we want to break x up into two pieces. One piece that's in W, and we call that the projection onto W of x, and the other piece that's perpendicular to W, and we'll call that x perp. Okay, so how do we find PW of x? So the idea is, as always, we want to write x as some linear combination of the basis vectors. So this is going to be PWX. So that's the part of x that's in the W plane, or the W subspace, plus something left over that's perpendicular to the W subspace. And then we're going to take, actually I'm going to write the x on the right-hand side. We're going to take this equation, we're going to take the inner product of B1 with this equation, and we get this. C1 times the inner product of B1 with itself, plus C2 B1 with B2, plus CK B1 with BK, and then we have plus B1 inner product with x perp, but that's 0 because x perp is perpendicular to B1 and to every other vector in W, equals the inner product of B1 with x. And if we took the inner product with B2 with the equation, we would get this. Inner product of B3, inner product of B4, inner product of BK. And now look what we've got. Each of these results gives us one equation for the variables C1 through CK. And we've got K of these guys, so now we have K equations and K unknowns. And we can write this in matrix form. In matrix form, it says that we have a matrix whose ij entry is the inner product of bi with bj, times a vector that are the coefficients c1 through ck, equals what you get when you take the inner product of b1 with x, b2 with x, b3 with x, bk with x. Now this is the same matrix we saw when we were dealing with non-standard inner products. This is the metric matrix G. So what we've got is that G times this vector equals this other vector. So the first vector, the vector of coefficients C1 through CK, must be G inverse times B1 dotted into X, B2 dotted into X, BK dotted into X. And now there are some very special cases where this turns into something very nice and useful. Special case number 1 is where the B's are orthonormal. Well, the B's are orthonormal. The inner product of BI with BJ is 1 if I equals J and 0 otherwise. So our metric matrix is just the identity. So the C's are the inverse of the identity times these guys. And that gives us back our formulas for decomposing in an orthonormal basis. C1 is the inner product of B1 with X, C2 is the inner product of B2 with X, CK is the inner product of BK with X. Now the next special case is where the vectors are orthogonal but not orthonormal. If they're orthogonal, then G is not the identity matrix, but it is a diagonal matrix. And G inverse is a diagonal matrix whose entries are 1 over the inner products. And what we get is that each coefficient of C is given by an inner product divided by the inner product of Bj with itself. That was how we did our projections normally. Now, if the B's aren't orthogonal and aren't orthonormal, then the G might be a complicated matrix and you have to solve some equations. But it works out reasonably nicely if we work in ordinary Rn with a standard inner product. Because then, whenever you have a bunch of vectors, it's always convenient to package them into a matrix. So we've got a basis B1 through BK. make an n by k matrix out of it. And I claim that the matrix G is just A transpose A, because A transpose is B1 transpose through BK transpose, and A is B1 through BK. So how do you multiply A transpose by A? Well, the ij entry of A transpose by A is the ith row of A transpose times the jth column of A, which is exactly the inner product of Bi with Bj. So our metric matrix is just A transpose A, and our equations become A transpose A times the column of C's is A transpose X, because if you multiply A transpose by X, the first entry is B1 transpose X, the second entry is B2 transpose X, the kth entry is BK transpose X, and the inner product of any vector with X is the same thing as the product of the row Bj transpose with the column X. Now remember, we're working in Rn, so all vectors are columns and their transpose are rows. So this is what this equation simplified to, and we can go ahead and solve things. So let's do an example of that. We're going to work in a space. We're sitting in R4, and our subspace is spanned by the vectors B1, which is 1, 1, 1, 1, and B2, which is 1, 2, 3, 4. And somebody gives us a vector 1, 3, 3, 5 and says, find the projection of X onto the subspace. So our A matrix, the first column is B1, 1, 1, 1, 1. Second column is 1, 2, 3, 4. A transpose has 1s across the top and 1, 2, 3, 4 across the bottom. And if we compute A transpose A, the entries are this row times this column makes 1. This row times this column makes 10. This row times the first column makes 10. And this row times the second column makes 30. 1 squared plus 2 squared plus 3 squared plus 4 squared is 30. And A transpose X works out to 1236. So now we have to solve the equations. 4, 10, 10, 30 times C1, C2 equals 1236. And when you have a 2 by 2 system, it's easy to find the inverse of a 2 by 2 matrix. The inverse of the 2 by 2 matrix is 1 over the determinant times you swap the 4 and the 30, and you take minus signs applied to the 10s. And you multiply it out, and you get 0, 6/5. So that means that the projection of X is 6/5 times B2, and here is 6/5 times B2, and X perp is what's left over. That works out to 1/5 minus 3/5, 3/5 minus 1/5, and you can check that that's orthogonal to 1, 1, 1, 1, and it's orthogonal to 1, 2, 3, 4. So there is our example.